All right, so now we're going to talk about the ideal transformer, which basically neglects those winding resistances that we talked about previously. Obviously, some things to note here. The ideal transformer is not expressed in terms of the mutual inductance. Rather, it's expressed in terms of the turns ratio. If you remember from the previous slides, we talked about how these N1 and N2 are basically telling us the actual physical number of times that this coil is wound around the core, right? So if we eyeball this, it will never be drawn this way. I want to make note of that. You're never going to see, this is specific to this textbook. You're never going to see a physically drawn larger number of windings. Typically, you'll just see two inductors that have the same old symbol with the four little loops, and you'll see something like this with some kind of dot convention indicating that these are wound around the same core. And then this could be, as big as 1 to 100. They're not going to draw, 4 turns here and 400 turns here, because that would just be unnecessary. Sometimes you'll see it where they really want to emphasize that it's a step up transformer or something, and you'll see something that looks, something like this, just to let you know that there's more terms on the secondary, but it's not necessary. So don't take this as the default. This just happens to be part of the textbook that we're looking at, where they decided to draw 8 turns on one side and 4 turns on the other. But normally you'll just see 2 inductors that look like this, and then you'll be given a turns ratio, okay? And so it's important to note that these these transformers are not characterized by this mutual inductance anymore. The mutual inductance is still there, but for an ideal transformer, we assume perfect coupling. So we assume that K equals 1. And instead of dealing with the mutual inductance and, drawing an impedance here with a dependent source and doing the same on the other side, we kind of just scrap all of that, because in ideal transformers, there are very specific voltage and current relationships, okay? So you can see that they write out the voltage across the primary as V1. We could also call it VP if we wanted to. And then they write out the voltage across the secondary as V2. And so there's a relationship between the voltage and the turns ratio for an ideal transformer. And that is that the voltage, I'll just call them V1 and V2 since that's what they're calling them. Let's just get rid of these. So V1 over N1 is equal to V2 over N2. Okay, so that's the relationship of the voltages to the turns ratio. Of course, we can rearrange this so that we see that V2 over V1 is equal to N2 over N1. And we talked previously about how that N2 over N1 is also equal to N, and that's called the turns ratio. And so what that basically tells us is that the ratio of the output voltage to the input voltage is the same as the ratio of the number of turns on the secondary to the number of turns on the primary. So that's a really important relationship that we kind of talked about a little bit earlier, but now we're going to actually get into solving some problems and building some circuits in SPICE that utilize this fact. And so what that basically means is, just for example, let's say I have a 1 volt, let's just say it's the sine of 2 pi ft, just sine of omega t, nothing fancy here, amplitude of 1, and I'm just directly driving a coil. Of course, I said that you can't do this, but we're assuming this is an ideal circuit, and it's driving a 1 to 5 step up transformer, and it's driving some load resistance, okay? What the voltage that I would see that would show up across this load would be 5 times the sine of 2 pi ft. That's just the nature of the step up transformer. We don't have to do any deeper analysis than that, and then we could determine the current flowing here and so on. Okay, that's the beauty of the ideal transformer. Since it's ideal, we can take away a lot of the steps of the analysis and just straight up analyze the turns ratio and see what kind of voltages and what kind of currents we're going to get. So that's the relationship for the voltages right here, that basically the number of turns on the primary or secondary to the number of turns on the primary gives us the voltage on the secondary to the voltage on the primary. The currents, however, have a different relationship, sort of an inverted relationship, we can write I1 times N1 is equal to I2 times N2. That's kind of your proof that a current into the dot here forces a positive current out of the dot here. So the way that they're defining the current is they're defining a current in and a current out of the dot on either side. And so you get this expression here, I1 times N1 equals I2 times N2. And if we rearrange this, we get that I1 or I2 over I1 is equal to N1 over N2. So it actually has the inverted relationship from what the voltage is doing. And there's a reason for that. It's because power is conserved from the primary to the secondary of the transformers. Okay, so if I step up the voltage, I can't also step up the current, because we know that power is the product of voltage and current, right? So if I have a voltage step up, I have to have a current step down. And so that's the conservation of power at work in the transformer. Okay, so you see that, for example, if I had a step up, like I said here, 1 to 5, the current that's flowing in the primary side, let's just call it I1, I2 would have to be 5 times smaller than I1. So I could write, we obviously saw the voltage got 5 times bigger. I would have to say that I2 is equal to I1 times 0.2, or I1 divided by 5. And that guarantees that power is conserved. I have the same amount of input and output power, okay? And in the next slide, we're going to explore that a little bit more, but I'll go ahead and end this video here, and we will talk about conservation of power in the next slide, and then we'll do a little example.